started here. I just wanted to say that when I was a graduate student at UCSB, some of the professors there, they didn't care about cheaters. If there's cheating going on, they kind of ignored it. They kind of ignored it because they figured, the way science and scientific method works, eventually those cheaters will be found out. It might take some time, but they're only going to progress up to a certain point, and then everything's going to fall apart usually, because it depends on how high up you get. But there are some instances where, there have been cases. In fact, this just came out, yesterday, I guess, the day before, and that is the CDC, Center for Disease Control. Center for Disease Control has been withholding data. That is, when people withhold data, you just think they're hiding data. That's normally what the scientists will think. Why are you hiding data? You don't want to make the data public. And so, then, that reminded me, I've heard of cases where there have been, really pretty famous scientists who withheld data, who, in fact, they tried to hide the data, because one reason they tried to hide the data was because it didn't fit their hypothesis. And if they had presented the data, their hypothesis would have been severely weakened. Or they tried to manipulate the data. They tried to manipulate the data to make it appear much better than it really was. And so there's this famous case, I remember. This is really actually pretty sad. This is a Japanese researcher who was working in the lab of a Nobel Prize winner. And she was found out that she had manipulated her data, withheld data, hid data, this kind of thing, and eventually was found out. And so this is back in 2014. Why do scientists commit fraud? And I understand why she committed fraud, because under heavy pressure, from the group that she was working in, plus the money that was coming in, they had to keep generating funds and this kind of stuff. But she was under such pressure, she actually committed suicide. And so this was a huge story back in 2014, is this researcher who was pretty well respected, went to good universities, and just ended up under that pressure, succumbing and then cheating on her, and paid some pretty heavy punishment for that. So, yeah. Was found guilty. I said there wasn't scientific police, but this was pretty obvious, falsifying data. Pretty obvious case. And she admitted to it. Here's another one, scientific misconduct, in other words, just scientific fraud. This one is another tragic story. This is, I guess, the son or daughter of the person. In 1987, my father, a scientist at the U.S. National Institute of Health, killed himself after a member of his lab committed scientific fraud, and he got caught up in the investigation. You'd think, why go to that extreme, But it's also to show, eventually things do get found out. And that sense. Okay, let me just do one thing really quick. So history is repeating itself. Now we're seeing this, CDC not publishing large amounts of COVID data. CDC under fire for allegedly withholding. Why did they withhold it? Because they withheld it because it might not agree with their, what they're trying to push at the time, their hypothesis or their narrative. I don't think the CDC is going to, go to the extreme of, what those two did, but eventually people find out. It might take time, but the truth will come out. And so, in a way, that's pretty tragic. But in another way, it just shows you that science has a way of self-policing itself, I guess. Okay, we're going to go back to this. Log me out. Did we leave off with the nomenclature problems, or where did we leave off last time? On complex. What complex goes with the coordination number? Okay. And then how far did I get? Did I get through octahedral? Linear? Okay, then I'm a little bit farther behind. All right, let me do that in just a second. Let me just do one thing here. Sorry. And we have linear complexes, right? And so let me give you two examples of linear complex. So for example, if I have silver ions, silver likes to form linear complexes. And how do I know that? That's just empirically. This is what's observed in nature. We have different Lewis bases that could attack. So, for example, ammonia, that lone pair attacks the silver here. Another one can attack over here. And so we'll have two ammonias attached to that. Now, the silver is a +1. The ammonias are neutral. And again, we don't worry about the way we counted formal charge earlier. We just say silver +1, two ammonias. That's going to give us a net charge of plus. It's a really linear complex. Now, we're going to get into the naming of these things. So I'll just tell you the name of this, and then we'll look at the rules for naming. It's going to be di, which means two, and then we have amine, which is the name we give ammonia when it acts as a Lewis base. These Lewis bases are also called ligands. And so we'll say these would be amines or ammonias acting as ligands or Lewis bases, or like this, and then silver. Now, we add a Roman numeral for the charge on the silver. The charge on silver is +1, so it's Roman numeral 1 ion. So this would be the diamine silver 1 ion. There's another complex that's quite common, and rather than ammonia, cyanide is a better one. Cyanide is a better one, it turns out, because did I talk about Lewis base strength in transition metal complexes? Carbon donor is the best. Carbon monoxide, cyanide. So cyanide's even better. And so we can attach two cyanides to this. This lone pair on carbon. There's also a lone pair on nitrogen, but nitrogen isn't as good of a donor. Not only that, the carbon, these are weird where carbon monoxide and cyanide have carbon in the -1 formal charge. Did I draw the Lewis structures for that last time? No. And so we have a choice when it comes to cyanide. It could be a nitrogen donor or it could be a carbon donor. When we look at the formal charge here, the formal charge on carbon is minus. Here. Formal charge on nitrogen is 0. Everything has an octet. And so this has a very weird formal charge. The very weird formal charge is normally we'd expect nitrogen to have a negative charge over carbon because nitrogen is more electronegative. The more electronegative element should have the negative charge or the negative charge density, but in this case it isn't. And so this is what makes cyanide an unusually powerful base. It's an unusually powerful Lewis base because of the carbon donor here. Now, as far as a Bronsted base goes, it's not. It's a moderately weak Bronsted base, but a very strong Lewis base. Carbon monoxide is also pretty strong. If we look at carbon monoxide can be an oxygen donor or a carbon donor. It turns out it's a carbon donor. Look at the formal charges. The formal charge on carbon is -1. And there's also a formal charge on oxygen. What is it? +1. This is very unusual. Why? It just seems wrong. It seems wrong because if there's a tug of war for electron, oxygen will win. In this case, carbon won. Why would carbon win? Well, actually, we can go ahead and donate that electron back to oxygen. One way we could do that is, let's see, we'll just make this a quadruple bond. Does that work? Or if we don't want to go quadruple bond, let's go double bond. Let's put 2 lone pairs here and 1 lone pair on the carbon. Maybe that would be better. When we look at this, this has 0 formal charge on the carbon and 0 formal charge on the oxygen. But there's a problem with this structure. What is it?
Octet.
Octet. Octet rule is violated, so we can't have this. And so this is in. And so both of these carbon donors will have a negative formal charge on it, a negative charge, which makes it a very good donor. And the carbon is going to be the better donor here. So what do we name this? Well, the first thing is, both of these cyanides are still -1. So again, even though it formed this bond and we wouldn't expect it to do that, it's -1, -2, +1, which gives us a minus charge here. Now, there's a big difference when the complex is negatively charged versus the complex is positively charged. There's a big difference in the name of the metal. And so when I have a negatively charged or an anion complex like this, okay, this is going to be dicyano or cyanido, either. Dicyano. And the name of the metal here is going to be argentate, not silver. Argentate. And the charge on silver is +1, so it's argentate 1. Dicyano, argentate 1 ion, or dicyanide, argentate 1 ion. So those are some examples of linear complexes. The next complex we'll take a look at will be tetrahedral. Aluminum is a 3+, and aluminum can be attacked by hydroxide. Hydroxide is a Lewis acid and a Bronsted acid. And so if we take 1 lone pair from the hydroxide and bond it, we'll have this. So another hydroxide can come along. Normally hydroxide has 3 lone pairs. One of these lone pairs will be used to bond. Actually, this doesn't look so tetrahedral. This looks square planar. But when we draw Lewis structures, we don't have to pay attention to the shape. And so what I'm going to do is I'm going to do the wedge dash drawing for this. And we'll just put the OHs like this. Now each hydroxide is still -1. Although when you look at this, this is a little water. So it's like water, there's no formal charge. Formal charge is level 0. So again, we don't follow the same kind of counting schemes. And we don't follow the same kind of bonding analysis that we do for other compounds with these complexes. And so this whole thing is -1, -1, -1, -1, that's -4 plus 3. And that gives us a negative charge here. So this complex here is named tetrahydroxido aluminate 3. So there's a distinction. Over here with this anion complex, I use this Latin name, argentate or arginium, rather than silverate. Silverate just traditionally has not been used. Over here, there's no fancy Latin name that I could use for this. It's just aluminum, aluminate. That's all we're going to have. And so I can tell that this is an anion complex by the ending of the metal. Whenever there's an 8 here, there's a net negative charge. 8, net negative charge. There's no 8 here. And so if there's no 8, then it's positive or neutral. That's tetrahedral. That has what we call coordination number 4. So when I look at linear complexes like this, we can look at the coordination number. It would be 2 over here. Over here in tetrahydroxide aluminate, the coordination number is equal to 4. But when we have a coordination number of 4, it could either be tetrahedral or it could be square planar. So let's take a look at some square planar complexes here. Now, how do I know it's square planar or tetrahedral? Well, this is just empirical data. It's by observation. And so I don't know, we just observe it, and that's what's observed. It's tetrahedral. So that one's observed as tetrahedral. However, this one, if we do platinum 2 plus and put 4 ammonias, it does not adopt a tetrahedral structure. The nitrogen is attached. That's why I'm writing the ammonia backwards for this left one. But this doesn't adopt a tetrahedral. This adopts a square planar structure. So this is just flat. Over here, it's not, this drawing's not accurate as far as 3-dimensional shape goes. This is okay. This whole thing is 2 plus. And so normally when we do VSEPR, valence shell electron repulsions, if we have square planar, that means there's a lone pair stuck on top and a lone pair stuck on the bottom, forcing these into square planar arrangement. In this case, there's no lone pair there. And so VSEPR and the way we count electrons doesn't work for these. So when we do VSEPR analysis, we would predict this to be tetrahedral. There are 4 groups, 4 single bonds. Spread out those groups as far apart as possible. It's going to adopt a tetrahedral structure, but it doesn't. There's reasons for this theoretically, but right now we're just on empirical. It's strictly empirical. And if I wanted to figure out, will the 4 coordinate, because this is a coordination number 4, this is also a coordination number 4. So if something has a coordination number 4, that means it's either tetrahedral or square planar. Which one is it? Well, we look it up in the book. At this stage, just look it up in the book. And you'll find that platinum 2 plus likes to be square planar or octahedral, which is the next one. Okay, naming this one here This one is called tetraamine. Now this amine has two M's, just like I wrote the silver one. There are amines with two M's and amines with one M. An amine with two M means ammonia as a ligand or Lewis base. Amine with one M means ammonia-like base, weak base. Anyway, this one's called tetraamine platinum. This is all one word. Roman numeral 2. Roman numeral 2 is because of the positive 2 on platinum. And then we have octahedral. Did I try to draw the octahedral complex of EDTA, lead? I did that?
Yeah.
Okay. Let's name that one. And so the formula for that one would be like this. In the formula, we write the metal first. In the name, we write the ligands first. So in the formula, it's going to be PB, and then we're going to write EDTA. We're allowed 3 abbreviations. EDTA is 1, that stands for ethylene diamine tetraacetate, or ethylene diamine tetraacetato if it's a ligand. In this case, it would be ethylene diamine tetraacetato. We're allowed EN. EN stands for ethylene diamine, and we're allowed OX, which stands for oxalate. These oxalate and ethylene diamine, I talked about bidentate ligands. Right? Those are bidentate. This is not a bidentate. What is this one? This is hexadentate. Now, the charge on ethylene diamine tetraacetate is what? 4 minus. And then lead is 2 plus. So this whole thing gets a charge of 2 minus. Now, we're going to name this by naming the ligand first, and we can't use the abbreviation for ligand, so we have to write it all out. Ethylene diamine. Now, this amine has 1 M or 2 M's? When we have 2 M's, it's ammonia. When we have 1 M, it's an ammonia-like compound. Now, ethylene diamine is ammonia-like, not ammonia. And so it's going to have 1 M. Ethylene diamine tetraacetato. We drop the E and then write O when it's acting like a ligand. Now, this is an anion complex, and so we have to use the 8 ending on the metal. So should we call it lead 8, or should we call it plume bait? Yeah, kind of which one sounds better? And it's going to be called plume bait. The charge on the lead is +2, so it's Roman numeral 2 here. So this would be the ethylene diamine tetraacetato plume bait 2 ion. This is what you want to form in, the lead poisoning cases. Because once you can encapsulate the lead ion in this cage, which would be the ethylene diamine tetraacetato, the cage formed from that, then you render it inert, towards at least the lead.
Can you go over why we started vacuuming with the living unit instead of starting it with lead?
You want to. I'd like to start it with the lead, but I don't know. Somebody came up with this scheme. Why? I have no idea. It's just somebody decided to do it this way. It's backwards. And so it always confuses students. And I see this on nomenclature quizzes where people write it first lead because that's the first thing that comes up, and then ethylene. So they'll call this lead 2 ethylene diamine tetraacetato or something like that. But based on the rules of nomenclature, it's backwards. So you always have to think it's backwards. You know, the formula and the name are reversed from each other. And so for the names for all of these, the metals at the end. You know. Some of these metals, though, we use the special name. You know, what metals are they? Well, you know, lead. We know if lead is in there, we call it plumbate. So these are for anion complexes. And so we don't call it lead, we call it plumbium, plumbate. Silver we call argentate. Gold we call orate rather than goldate. This would not be silverate, goldate. Instead, argentate, orate. Tin we call stannate. Iron we call ferrate. And that's pretty much it, I think. Let's look at some other octahedral complexes. Another octahedral complex would be this. We could do NH2, CH2, CH2, NH2. Do you recognize what that ligand is there? Yeah, this is ethylene diamine. So we have ethylene diamine there. Let's do another one. Some people do use an abbreviation like this. And so they put an ethylene diamine like this. And let's do another one here. I'll use the abbreviation. And so it looks like I have 3 ethylene diamines. If I were to write out the formula, ethylene diamines are neutral, and we're going to keep this as lead 2+. And so the formula for this is we write the metal first, and then we have 3 of the ethylene diamines. Now in the formula, we could abbreviate it like this, and we have 3 of them. It gives us a 2+. What's the coordination number of this? Well, a lot of people will say the coordination number is 3 because we have 3 ethylene diamines. Therefore, it's got to be coordinated with 3 ethylene diamines. But what they're forgetting is that each ethylene diamine is bidentate. And so really the coordination number is 6. Coordination number of 6, we only have one choice, it's octahedral. That's it. Okay, let's name this. When we name this, I'd like to name this triethylene diamine. Lead or plumbate? How do I know which one it is? Should I call it lead or should I call it plumbate? I need to call it lead because this is a positive and neutral complexes. We don't change the name. And so we just call it lead. And the charge on lead is 2, so we'll write that in Roman numeral here. And so this is the triethylene diamine lead 2. But there's a bit of confusion here. And the bit of confusion is this makes it sound like I have 3 ethylenes and 2 amines. So if somebody were talking to you and they said, okay, triethylene diamine, you might think, without seeing it, because how do you know if it's 2 M's or 1 M? If somebody just said triethylene diamine, you don't really know. And so there's a bit of confusion because you might think we have 3 ethylene molecules and 2 amines, ammonias. But that's not what we have. And so what we need is we need to do an alternate numbering system because I have the numbering here because I have 2 amine type groups. But rather than using tri here, what we do is we use a secondary numbering system, tris. Tris means 3, and so we'll just say tris ethylene diamine lead 2 ion. So tris ethylene diamine lead 2 ion. Okay, some people will go this far to emphasize that we have 3 ethylene diamines and not 3 ethylenes and 2 amines. And so they'll put parentheses around this here. Oops. And so we don't use abbreviations for the name. The name we have to spell out completely. We can use the abbreviation for the formula, like here, but when it comes to the name, I had to write it all out. Ethylene diamine tetraacetate. Same thing over here. We could use the abbreviation for the formula, but for the name, I had to spell it all out. Tris ethylene diamine lead 2. All right, so what we're going to do is we're just going, rather than going through the step-by-step rules, we're just going to look at examples of nomenclature and writing formulas and see if we can figure out a set of rules for ourselves. All right, try this one here. Write the formula and name of a complex ion having chromium 3 as the central ion and 2 ammonia molecules and 4 chloride ions as ligands. And so I'll give that one a shot. And then pause this. So we just did this one. Now we're doing the next one. So whenever we have a coordination number of 6, it's octahedral. And so we're going to have an iron 3 in the center. And then what I do is I'll just draw an octahedral arrangement of bonds here. And then put 6 cyanides on there. Sometimes you write these backwards just to emphasize that the carbon's bonding, not the nitrogen. And so that's why these cyanides are backwards. What's the total charge on this? Yeah, 3 negative. So it's an anion complex. That means we have to do something funny with the metal. And so what did you get for the name? Yeah. Hexocyanoferrate 3. That's correct. Wow. That's good. Cyanide is a very good ligand, and so binds pretty strongly to the iron. So you wouldn't think of this as being especially toxic,
So for this structure, it's really using this on the exam. In fact, would the structure be correct that you have on the left side where the C's are? If we put on CNN, would that be incorrect? Yeah. It's not at all?
No. So you wrote it like this?
Yeah.
No, I wouldn't mark it wrong. You know, what would be good is if you could just kind of offset it a little bit so it looks like the carbon's bonded there. But it doesn't matter. You get that. going to do is we're going to just get a lot of practice. So what I'm going to do is I'm just going to go through these quickly here, also to catch up. And then we'll go through all the nomenclature and formula writing problems, all the other ones. And so look at C, a coordination compound comprising two types of complex ions. One complex of chromium-3 with ethylene diamine, having a coordination number of 6. The other, a complex of nickel-2 with cyanide, having a coordination number of 4. And so let's take a look at the first complex here. It's going to be a complex of chromium-3 and ethylene diamines. So it's chromium-3 with a coordination number of 6, containing ethylene diamines. So this is very similar to what we looked at earlier. And so here I'm going to use the abbreviation for this rather than write it out. Here I'll just write it out. Here it's going to be NH2, CH2, CH2, NH2. So for this one, I'll just use the abbreviation EN. And so if I have a coordination number of 6, how many ethylene diamines can I fit around there? 3. And so the formula is going to be metal first, followed by, now I can use the abbreviation. I can use the abbreviation for ethylene diamine oxalate, or oxalato, and ethylene diamine tetraacetato. This is going to have 3. What's the charge on this? 3 plus. Yeah, ethylene diamines are neutral. Right. Then the other complex is going to be nickel-2 with a coordination number 4. Nickel-2 likes to form square planar complexes. How do I know? That's just what's observed. And so it's going to be a square planar complex. How do you know? You look it up. You see, oh, nickel-2, square planar. Later on, we'll kind of try to look at a little bit of the theory. And the theory is D8. D8 means 8 d electrons. They like to be square planar. They like to be square planar because that gives the lowest energy orbital configuration. But for this one, with cyanides, so here I'm just going to write it CN rather than NC. But most people will write it NC backwards to emphasize that it bonds. So it doesn't matter. Okay, the nickel is 2 plus. That means the complex has a has a total charge of what? There are 2. Yeah, that's one. The other way we can know that carbon's a better donor than nitrogen is because of the formal charge. To be a good donor, you want to be as negative as possible. That is, have as big of a negative charge as possible. So which atom has a bigger negative charge, carbon or nitrogen? Now, if you just use electronegativity, you can say nitrogen does, because nitrogen is more electronegative. It's going to pull the electron cloud closer to it. But when you look at formal charge, no, it's not nitrogen, it's carbon, because the negative charge on cyanide doesn't end up on nitrogen. The negative charge on cyanide ends up on carbon. Nitrogen's got 0 formal charge. And so there are 2 reasons. One, carbon's the best donor, and 2, this carbon has a negative charge, making it even better than this one. So carbon's much more willing to give up some electron density in this case. So when we write the formula for this one, it's going to be Ni parentheses CN4, and the charge 2 minus. And so this is an anion complex. So we're going to put these together to make an ionic compound. So our cation is 3 plus, our anion is 2 minus. when we put them together to make a ionic compound, we're going to need, looks like we're going to need 2 of these and 3 of these to balance out the charge, just cross multiply. So 2 of the 3 plus, so that's going to give you CREN, 3, 2. That gives us a total charge of plus 6. And then 3 of these nickel complexes, which will give us a total charge of minus 6. And so the charge is balanced. If I have 2 of these plus 3s with 3 of these minus 2s, then I'm electrically neutral. And this would be the formula. Now, this is not an ion. This is a compound. And it's an ionic compound. It's just got some weird ions. And so let's name this. What's the name of the first one? Is the first one triethylene diamine or trisethylene diamine? The first one's going to be tris. That's because ethylene diamine has one numbering system, the di. And so if we don't want to use the same numbering system to number how many ethylene diamines we have, so we're going to use a secondary numbering system, tris. And it's going to be ethylene diamine. Diamine's 1M. Chromium, or chromate. Chromium because it's the cation. And the charge on chromium? 3. So that's the name of the cation. The name of the anion, we'll do space, and then name the anion. The anion will be tetra, cyano, nickel or nickelate? Nickelate. Tetracyanonickelate, and the charge on nickel? Yeah, plus 2, so Roman numeral 2. So this ionic compound has this strange name, trisethylene diamine chromium 3, tetracyanonickelate 2. It's a funny name to it. Because ethylene diamine already has di, and so that's our primary numbering system, di, tri, tetra. Since ethylene diamine already has di in it, then if we're going to number these, how many of these ligands we have, we should use a secondary numbering system so that we don't get it confused. And so the secondary numbering system would be tris. So tris tells us how many ethylene diamines we have. If I use the primary numbering system for both, that is, I do triethylene, diamine, this, because of the numbering system, this makes it sound like I have 3 ethylenes. Ethylene's a molecule, and 2 amines. Amine is like ammonia. Although this is not ammonia because ammonia would have 2 M's, but if you're just talking, how do you know? And so to avoid this confusion, if the name already has the primary numbering system in it, then we should use the secondary numbering system to number how many we have of that. Uh-huh. Okay. What if we had this? What if we had 2 of these? OX stands for oxalato or oxalate. And so if we have 2 oxalatos, how do we name that? Should I use the primary numbering system, di-oxalato? Or should I use the secondary numbering system, bis-oxalato? Should I use the primary di, or should I use the secondary bis? Okay, the answer is that we should use the primary. Why? Because we haven't used it yet. And the primary is not used in the name. Oxalato doesn't have any numbering system within the name. Whereas over here, ethylene diamine, that's the name of the ligand, already has the primary numbering system in there. So if we're going to number how many of those we have, 3 of them, then we better use a secondary numbering system for that. And so we always start off with the primary numbering system first. Here. And so it would be dioxalato if we had 2 oxalates. Okay, let's take a look at some of these others. How would you name this one here? Do we name cobalt first or amine first? Well, it's always, when we do the name, the ligand is first. When we do the formula, the metal is first. Remember, they're opposite. So if you see the metal first, then the name's going to have the ligand first. And so this is going to be amine first. But how many amines do we have? 6. So that would be hexamine, cobalt or cobaltate?
Cobalt.
Cobalt, and the charge on cobalt? 2. So that would be all one word. Hexamine with 2 M's, cobalt 2 ion. Okay, how about B? Hexafluoro. Is fluoro spelled F-L-O or F-L-U? F-L-U. F-L-U-O-R-O. You could call it hexafluoro or you could call it hexafluorido. The latest edition of our book would call it fluorido. The older edition of our book would call it fluoro. What you're going to see is you're going to see more fluoro than fluorido because fluoro has been around for a lot longer. So hexafluoro, aluminum or aluminate? Aluminate, 3. That's correct. There's 3 plus on the aluminum, minus 6 for the fluorides gives us a 3 minus. C. Actually, I forgot one. Copper is either copper or cuprate. So this would be hexacyanocuprate 2. That's correct. Now, the 2 Roman numeral does not refer to the net charge. The 2 refers to copper plus 2. How do you know it's copper plus 2? Because you know cyanide. Cyanide, E cyanide is minus 1. Therefore, this is going to be minus 4. Minus 4 plus what gives us minus 2? It's going to be plus 2. And so the Roman numeral comes from the plus 2 charge on copper, which we figured out looking at the formula. How about this next one here? Now, when we do the ligands, we write the ligands, the anion ligands first, followed by the neutrals. And then if we have more, then we do go alphabetical. And so here, when we name this, we don't care if it's an anion or neutral. We're going to name it based on its alphabetical order. And the alphabetical order could be based on the B or the N or the H. But we're not going to do that. We're going to base it on the name. So bromo or bromido with a B or amine with an A. amine with an A. So we'll do tetraamine with 2 M's, di, bromo or bromido, chromium. Now what's the charge on chromium? Well, the whole thing carries a charge of +1. Ammonias are neutral. Bromide is -1. So -1, -2, -2 plus what gives us +1? It's got to be +3. So this is going to be chromium 3 or chromate 3. Yeah, chromium because it's got a net positive charge.
We can start naming in alphabetical order one.
Alphabetical order in the name?
Yeah.
Yeah, always alphabetical order for the name regardless of charge. And we're going to do alphabetical order based on the name, not the formula. If you look in the book, it's based on the formula. But there's some confusion depending on how the formula is written. And so to do this, let's just go with this. If you have more than, let's say, one anion, let's say you have bromine and chlorine, you'd write the chlorine first. Well, or no, you'd write the bromine first, followed by the chlorine, because B comes before C. That's what you do. Okay, let's look at E. E is going to be trioxalato or trisoxalato? Trioxalato. Cobalt or cobaltate? Cobaltate. Trioxalato cobaltate. Now we got to figure out the charge on cobalt. So each oxalate has what charge? Each oxalate is -1, 2. Actually, -2. Each oxalate's -2. -2 times 3 is -6. -6 plus what gives us -4? 2. So it's got to be cobaltate 2, Roman numeral. Okay, do you know what S2O3 is? Sulfate?
No, silicate.
Silicate is Si. Silicate is SiO44 minus. Let me tell you, there are some other nomenclature tricks. Do you know what sulfate is? Yeah, that's sulfate. You know what sulfide is? SO3, 2 negative. Do you know what thiosulfate is? Thiosulfate. This is sulfate. If we look at thiosulfate, thio means replace one oxygen with a sulfur. Replace one oxygen with a sulfur, same charge. That's thiosulfate. So if we look at the structure of sulfate, let me do the most common structure of sulfate with an expanded octet. This is a violation of the octet rule. Oops. You know, but if you look in Chem 1A, Petrucci, the end of the bonding chapter, he talks about the, maybe it's not an octet rule, maybe it's an octet law. Law being strictly adhered to anyway. But it's okay. Here, so what I'm going to do is I'm going to replace one of the oxygens with the sulfur. Actually, all 4 of these oxygens are the same because we get our resonance forms, and the hybrid would be the true structure. But if I replace one of the sulfurs, one of the oxygens with the sulfur, let's replace this top one here. we end up with a thiosulfate. This is thiosulfate here. Now, sulfate itself, as far as redox properties go, is only an oxidizer. It's maxed out. Sulfur is in the oxidation state of +6 here. Oxygen is going to take all the electrons. These are the none, so +6. Oxidizer. Thiosulfate is known as a good reducer. It's known as a good reducer because of the sulfur. The sulfur, well, you look at the oxidation state of the sulfur, 1, 2, 3, 4, 5, 6 is 0. But sulfur, elemental sulfur, makes a good reducer. It's not too difficult to burn. And thiosulfate itself is a reducer as well. Now we got to ask ourselves: is thiosulfate square planar like this or tetrahedral? Here, Vesper works. So we have 4 groups. 4 groups are going to adopt tetrahedral configuration. So these 2 oxygens are actually adjacent to each other. All the angles are 109. So these are sticking out, perhaps. Okay, the next thing I'm going to ask you is this. Is thiosulfate a monodentate, bidentate, tridentate, or tetradentate ligand? Mono? Okay. Mono is correct. Why not bidentate? So if I had a metal here, why not bidentate? Yeah. It would form what? A 1, 2, 3, 4 atom ring. 4 atom rings are highly strained. And so it's not going to be a bidentate or tridentate. It's going to be just a monodentate. And so this is just going to be a linear. In fact, silver complexes are usually linear. And so we're just going to have a silver here. This lone pair is going to be used to form the bond. And so we'll just have 2. Now, the sulfur can also be a donor, but I would suspect the oxygen would be a better donor because of the negative charge density on that. But sometimes the sulfur can donate as well. So we have that. What about the name for this? How would you name that?
Dithiosulfate?
Yeah, dithiosulfate. But since it's an anion, we change the ending. Whenever we have an anion, thiosulfate is going to be changed to thiosulfate O. So this will be dithiosulfato. Silver or argentate? Argentate. And what's the charge on silver? +1. Yeah, +1 is correct. Actually, silver only has 1 charge, and that 1 charge is +1. Uh-huh. It's an anion. Oh, like chloride gets changed to chloro or chlorido. Sulfate gets changed to sulfato. Thiosulfate gets changed to thiosulfato. It's just a convention. Okay, let's name this next one. Actually, before we name this next one, I guess it's time for a break. Let's take a break now, and then we'll finish these off. Okay, we'll get started again here. So supply acceptable names for the following. What is the, well, actually, before I get to that, actually, let's go ahead and try to name the first one. Now, what is this chlorine here? There's two types of chlorine. Did I talk about Werner yet? No? Okay. When I look at this chlorine is actually just a normal chlorine ion. However, the cation is not normal. The cation is what we call complex cation. And so if we have something like this, the way I see this is I have a +1 cation because I have a -1 anion here. And so the name of the anion is simple. This is just chloride. And so this is an ionic compound where we have the cation, we'll put the cation name followed by the anion name. We don't have to say monochloride because whenever we have an ionic compound, we can figure out how many chlorides we have based on the charge. And so here, what's the name of this cation though?
Diamine silver 1.
Yeah, so this would, the name of the compound would be diamine with 2 M's, silver 1. And so the name of the cation is this, the name of the anion is this, the name of the ionic compound would be diamine silver 1 chloride. Now we have to differentiate between chlorides that are outside the coordination sphere. You know, what is the coordination number of silver here? The coordination number of silver is 2. Some people might say 3 because of the chloride. They think, oh, the chloride's going to be coordinated. No, the chloride's going to be coordinated with this cation, this big cation here. And the chloride's actually not covalently bound to the silver. It's ionically bound to this big cation. Okay, this distinction brings up, let me talk a little bit about the history of complexes now. Alfred Werner won the Nobel Prize for his work on the structure of these complexes. And so let me talk a little bit about section 24.1. And if we look at something like this, you know, like a hydrate. How would you name that? This would be calcium sulfate dihydrate. Calcium sulfate dihydrate. And hydrates occur when water from air is attracted to the ions. Water is going to be attracted to the ions because water is polar. There's a negative end, which is oxygen, a positive end, which is hydrogen. So it's going to get attracted. And sometimes these waters will stick onto the surface of the crystal. So if I have a calcium sulfate crystal, the water gets stuck on the surface. And sometimes these waters can wiggle into the structure itself. The waters can wiggle into the ionic lattice and occupy holes in the lattice. Do you guys remember holes in the lattice? Octahedral holes, tetrahedral holes, interstitial sites? No? So you have, let's say, a crystal of calcium sulfate here, and the waters get stuck on the surface, and eventually they can wiggle into these little gaps between the ions. And so there are going to be gaps between the calcium ions and the sulfate ions. Those are called holes, and the waters can wiggle in. And so when this is saturated, all the holes are saturated in calcium sulfate, we can hold a max of 2 waters per formula unit of calcium sulfate. And so those get in. And that's what we call a hydrate or hydrated crystal. This is like a sponge. You know, the sponge has holes, and those holes can accommodate the water. And so this would be like a saturated sponge. However, it's a solid, you know, well, just like the sponge is a solid. Sometimes it doesn't even look wet. Calcium sulfate is what we call dryerite. Dryerite's this white stuff, and what dryerite is it's used as a desiccant. It's used to suck water moisture out. So let's say, you know, have you seen those little desiccant packs they put in like shoes or other things? They want to keep the humidity down so no mold or whatever grows, you know, at low humidity. And so this is a desiccant. You can't tell, you know, if it's been hydrated yet, because the hydrated form looks the same as the desiccated form or the anhydrous form. And so in dryerite, this is a commercial name for calcium sulfate, they put a dye, and this dye is moisture sensitive. When it's dry, it's blue. When there's moisture present, it's pink. So if it turns pink, then we have to dry it. The way you dry it is you just throw it in the oven and you force the water out of the pores or the holes, and then it goes and turns back blue. You might have used desiccant in Chem 1A. Actually, you probably didn't, because none of you did any of you do the lab for Chem 1A? Yeah, then you use the glass desiccator with dryerite at the bottom for the calcium, for the sulfate samples. Okay, so that's fine. So there are others. For example, this. Copper sulfate also forms a hydrate. And if we look at copper sulfate, it can absorb 5 water molecules per formula unit of copper 2 sulfate. Copper 2 sulfate doesn't need a dye. It's very easy to tell if it's hydrated or dehydrated, just based on the color. No, I'll do it this time. The hydrated form of copper 2 sulfate has these very nice blue crystals. It's a solid. You can't tell it's wet, but it's wet because there's 5 waters for every formula unit in there. If you were to heat this up, so here's some nice blue crystals. This image isn't so great. And then they heat it up. This is the dehydrated form. The dehydrated form of copper 2 sulfate is this off-white color. And then it's slowly rehydrating. It's slowly rehydrating. You can see the light blue color develop there. It's slowly rehydrating by picking up moisture from the air. And so they're just evaporating it in an evaporating dish here. That is, they're evaporating off the water. And so this one's easy to see. There's another way to free up the water or get rid of the water. You know, one way we could dehydrate this. Another way is we could dissolve this in water. If we dissolve this in water, what happens is sulfates are mostly soluble except for silver, lead, mercury, calcium, strontium, barium. And so this is soluble. And what the water is going to do is it's going to break apart the lattice and free up the ions. So we're going to get copper 2 ions. We're going to get sulfate ions. And then the waters are just going to break free. You know, the lattice is going to be broken apart. And so this is just going to break the waters free. So here's the ionic lattice. You see the copper 2 and the sulfates of these yellow and red things here. And then the waters are incorporated into the lattice itself. And then we dissolve this, break apart the lattice, free up the waters. All right, so this is our current picture of what's going on here. And so now let's take a look at something like this. If I have this cobalt chloride dot cobalt chloride dot 6 ammonias. Ammonia is very similar to water in that it likes the hydrogen bond. Ammonia is very polar. And so if we have ammonia gas molecules in air, those ammonia gas molecules will stick to the surface of the crystal and eventually wiggle their way into the little holes in the crystal. And so this is the equivalent of a hydrate, except rather than using water molecules in hydrating, we're using ammonia molecules. And these ammonia molecules are going to do the same thing as the water molecules. Okay, then we can, chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So this will dissolve in water. So we dissolve this in water, that's going to free up the cobalt ions, free up the chloride ions, and free up the ammonia molecules. We get 6 ammonia molecules here. Ammonia is very soluble in water, because it's quite polar, can hydrogen bond to water. So this will be aqueous, 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 aqueous. Then we're going to do a test to detect chloride. So tell me some chemical properties of chloride. Start off with acid base. Is chloride a very good base? No, it's an awful base. Chloride's a reducing agent. Is a very good reducing agent? No, it's pretty awful reducing agent. It's not very good reducing agent. It's pretty stable. You can eat the stuff. What about the metathesis properties? Does chloride have any metathesis properties? Yeah, what cations does chloride like? Silver. Yeah, silver, mercury, and lead. And so what we're going to do is we're going to add excess silver ions to this, like silver nitrate, dump some in there. And what should form? Silver ions like chloride ions, and it should form a precipitate, a white precipitate of silver chloride. And this. So if I have 3 moles of chloride, how many moles of silver chloride should I form? 3, right? It's 1-to-1 mole ratio. And so that's what's expected. And actually that's what was formed. 3 moles of chloride. Now the max ammonias we can fit in that lattice of 6, but we don't have to saturate it. It's like a sponge, you know? A sponge doesn't have to be saturated. You could like half saturate it or partially saturate it, you know? So it would be unsaturated. So what I'm going to do is I'm going to do the same thing, except we're going to use less ammonia. And so I'm going to expose it to less ammonia. If I expose it, then there's going to be some vacant sites, you know. So here, rather than getting 6 ammonias to wheel away in, we'll just get 5. There'll be one empty site, you know. There's room for 6, but we'll just have 5 in there. Yeah. And so, you know, naming these would be kind of weird. It would just be .5 ammonia, cobalt, solid. So if I dissolve this in water, I'll break apart the lattice and form the ions, cobalt 3, 3 chlorides, and now 5 ammonias will escape, you know, because lattice is going to be broken apart. They're no longer trapped in the lattice. Okay, now I'm going to add the excess silver ion. And so for every 3 chlorides, how many silver chlorides do you expect? For every 3 chlorides, how many silver chlorides will I get? 3, yeah. So we expect 3 silver chlorides here to precipitate for every 3 chlorides. This was expected. But it turns out it was wrong. Do you know how many chlorides were actually obtained? No. 3 were expected, 2 silver chlorides were observed. What happened to that 3rd chloride? Only 2 out of the 3 precipitated, leaving 1. Even if I add excess silver, I don't capture that. And so what happened to it? And so this was a mystery. And so this is the reason why Werner won the Nobel Prize, because he figured out the mystery. Do you know what the mystery is? The mystery is, this is probably not the best way of writing this. So what Werner did was he did this. He rewrote these formulas to more accurately reflect the structure of these. And so this one should be rewritten like this. So if I take this solid and dissolve it in water, what does it dissociate into? Now, when I look at this, what do we name this? You know how to name this here. What is this name? Hexa, amine, cobalt 3. And so when I look at hexamine cobalt 3, ion, that would be it. When you dissolve it in water, are you going to break the coordinate covalent bonds? Are you going to break the dative bonds holding the nitrogen to the cobalt? And it turns out when you dissolve it in water, you don't break the covalent bonds. You break the ionic bonds. What are the ionic bonds? The ionic bonds are holding the chlorides. And so the ionic bond is going to be between the negative chloride and the positive cation here. And so this makes a lattice. And so for every one of these cobalt cations, I'm going to have 3 chlorides that are going to be ionically bonded to this. We don't show the ionic bond with a line or anything. We just show it by having the ions adjacent to the cation. And this is going to go off in 3 dimensions, etc., etc., etc. And so we have a solid crystal of this. Now, when we dissolve this in water, we break the ions apart. We do not break the covalent bonds apart. We break the ionic bonds apart. And so what we end up with is this. The hexamine cobalt, 3 ion, and 3 chlorides. And so the chlorides will separate from the cation. We have that. Now when we add excess silver nitrate, or silver ions, we're going to get 3 silver chlorides. Okay, what's happening here is cobalt. What's the coordination number of cobalt? 6. What's a better donor, nitrogen or chlorine? Yeah, a nitrogen donor or a halide donor? Nitrogen donor is better. And so nitrogen is preferentially going to bond to the cobalt, not the chlorines. And so if I have 5 amines here, those 5 amines are going to preferentially bond here. It doesn't matter where you put them. And then I'll put 1 chloro ligand on there. So really, what the formula for this should be is this. It's going to be CO. Now, what's written first, the chloro or the amines in the formula? The chloro, because it's anion. Anions are written first in the formula, so it's going to be COCl and then the 5 amines. And then the charge on this is going to be, well, cobalt's 3+, so the charge on this will be 2+. And if it's 2+, how many chlorides are we going to need? We're going to need 2 chlorides to balance out the charge. And so what we're going to get is we're going to get this as our 2+, and then we're going to need 2 chlorides to counterbalance out the positive 2 of the cation. Like that. And so now we see this lattice. It's going to go on, etc. So now when we dissolve this in water, what are we going to get? Actually, I should have left that bit, sorry. When we dissolve this in water, the ionically bonded chlorides will dissociate. But this chloride here is not ionically bound. This chloride is forming a dative covalent bond or a coordinate covalent bond. And so this is a covalently bonded chlorine. This covalently bonded chlorine doesn't break off. And so what I'm going to get is this. I'm going to get this cation. How do we name this cation? Here. The name of this cation is, well, we do it alphabetically. You know, amine or chloro. Which one gets named first? Amine. So this would be pentamine, chloro, cobalt or cobaltate? Cobalt. And the charge on cobalt? 3. 3 is correct. And so this ion is going to break apart from the chlorides, and then we're going to end up with 2 chlorides here. So now when we add excess silver ion to this, how many silver chlorides are we going to precipitate? Only 2. So Werner figured out the mystery. The mystery was these chlorines aren't equivalent. Two of these are ionically bonded. One of them is covalently bonded in the complex. And the coordination number is 6. And these are good ligands. Here. And so there's more, a little bit more to it. This is essentially won the Nobel Prize for this. How do we name this? Well, the name of this is just the name of the cation and the name of the anion. So it would be, pentamine chloro cobalt 3 chloride. Okay, not dichloride, but just chloride. This one would be hexamine cobalt 3 chloride. In this case, we have 3 chlorides. In that case, we only have 2 chlorides. But we have 3 chlorines here and 3 chlorines there. But the chlorines aren't the same. One of them's the ligand, the other 2 are just counter ions. So, in reality, okay. You good? Okay. So in Chem 1A, you learn to write it like this. CuSO4.5H2O solid, and we call it copper 2 sulfate pentahydrate, or copper 2 sulfate .5 hydrate. But in Chem 1B, you would write it like this. How would you write this? Let's take a look at what they're doing here. Oh, 1, 2, 3, 4. The 5th water. Interesting. When I take a look at that structure there, here, let me blow it out. You see, I'm looking at a square planar complex here. This is the copper, and how many aquas are there? 4 aquas. So it looks like. And then the sulfates are just hanging around the cations. You see the sulfates? They're ionically bonded. The sulfate would be out here. And then one water looks like it's trapped in the lattice. And so if I look over here, you see there's one water that's covalently bonded here, and this other water behind it is kind of stuck in the lattice. It's not bonded to anything. And so that's in a hole. And so it looks like this. The correct formula for this, and there is still work going on with this because some people say it's a penta complex, coordination number 5. But looking at this structure, it looks like a coordination number 4. So this would be tetra aqua copper 2 sulfate monohydrate. Kind of weird, right? But that's what we see. So this is an odd compound. But this is an ionic compound. The chloride's not in the coordination sphere. It's outside of the coordination sphere. This is just an anion, chloride. It's not a chloro. This is chloride. Okay, let's go on to the next one. When you dissolve this in water, what's going to form? Well, you think silver chloride's insoluble, but this diamine argentate, or not argentate, diamine silver 1 chloride is actually soluble. And what breaks apart is this cation from that anion. But we'll look at those more later on. Okay, what about this? Is this a sulfate or is this a sulfato? Sulfato would be bonded to copper. Sulfate would just be some anion, counteranion. Yeah, this would be a sulfate, just some counteranion. So what's the cation name here? Well, look at what they did here. We have two neutrals. One is aqua, the other is amine. LMNOP, So here's where it got us. You know, they're doing it alphabetical, H versus N. We're just doing it based on name. If we're doing it based on name, then I would have put amine before aqua. You'll see it both ways. With complexes, the nomenclature rules are kind of all over the place, so there's a lot more variation in these. But anyway, let's go ahead and name this. How would you name this one, the cation? Yeah, tetraamine diaqua, copper, or cuprate. Copper. What's the charge on it? 2. 2 is correct. Sulfate's a 2 minus. This is neutral, neutral. This has got to be a 2 plus. And so it's tetraamine diaqua, copper 2, sulfate. Okay, how about C? This is kind of a weird one. What this is it's a complex molecule or complex compound. This is not an ion. It's a neutral. In neutral, they aren't writing the square brackets because it would be square brackets with a 0 for the charge. So they just skip it. And so we're just going to name it the regular way. We name the ligands first, and they're going to be alphabetical regardless of charge. And so what would come first, chloro or ethylene diamine? Yeah, so we would go dichloro, ethylene diamine, platinum or platinate? Platinum, and the charge on platinum, 2. Is ethylene diamine's neutral, chloro is an anion. This one is actually a famous compound. So let me talk about this one. Platinum 2 complexes are square planar. How do I know? I just looked it up. And that's what's observed. Looking it up is what's observed. And so in this particular complex, we could have isomers. And what were isomers again?
Same formula.
Yeah, same formula, different structure. And the structure of this is square planar. So it's flat. It's not tetrahedral. In tetrahedral, we don't have this type of isomer occur. So the chloros, we can put the chloros. Oh, actually, let's see. This is not the famous compound, sorry. It's very similar to the famous compound. Let me talk about the famous compound here. The famous compound is this. It's the famous compound. There. Anyway, can you name this one? Let me just take this. Okay, sorry about that. So, what would the name of this one be? This one would be diamine with 2 M's, dichloro, platinum, 2. Okay, we add another part to this name. We're going to talk about this later. This time we don't have to worry. Cis. This is cis-diamine dichloro platinum 2. We also have something called the trans. The trans would look like this, where we have platinum here, and a chlorine here, and a chlorine here. So these 2 chlorines are adjacent to one another. These 2 chlorines are opposite sides of one another. And so this would be the trans diamine dichloroplatinum 2. This would be the cis. This has another name. This is called cisplatin. Cisplatin has an interesting history. And the interesting history comes from this research group at the University of Michigan. This research group, they're looking at ways of killing cancer cells. So one of the things they tried to do was try to use electric fields to cancel, or not to cancel, but to kill cancer cells. And the way they generated the electric field was they had electrodes. Electrodes, you know, they charge one electrode positive, the other electrode negative, and then they can generate electric field, positive on one end, negative on the other end. And what they did was they stuck these electrodes into like a petri dish of cancer cells. We call it the medium. And so they stuck it in there, and then they turned up the voltage. The higher the voltage, the greater the electric field. So they cranked up the voltage. So one thing is, why did they use platinum? Platinum's really expensive. Do you know why they use platinum? Because platinum is fairly inert. You know, platinum is really hard to get to react. You know, metals are electron rich, but platinum doesn't want to let go of any metals. Excuse me, not metals, of any of its electrons. And so platinum is extremely hard to oxidize. And so this is why when we crank up the voltage, you expect these to be fairly inert and unreactive. The odd thing is that the platinum started to react with the medium, which is some mixture. And whatever it was forming in the reaction, it killed all the cancer cells. And so there's some kind of chemical reaction happening between the platinum and the medium with the electric current. And so they wanted to analyze what the products of that reaction were. But the problem is if you have a complicated mixture, it's really hard to isolate what the product is, because there's so many things in that mixture. And so you could try a whole bunch of physical separation techniques. What are the physical separation techniques? Would be like filtration, distillation, chromatography, et cetera, et cetera. But the thing is, when you start doing physical separation techniques, you lose a little bit. You lose a little bit here, you lose a little bit there. You know, you have little losses. And since you're generating so little of the platinum compound, because, you know, platinums are fairly unreactive, it's really hard to isolate, because by the time they did one separation, it's all gone. And so unless they could synthesize like grams of the stuff or pounds of the stuff, then there's a chance, but they couldn't. And so you know what they did instead of separating the mixture to isolate the product and figure out what the product was that was killing the cancer cells? Do you know what they did? They ended up opening a chem catalog and buying every platinum compound they could buy in the catalog. And they bought every platinum compound they could buy and then tested those individually against the cancer cells, and they found it. They found this. The cisplatin was killing the cancer cells. And so eventually what they did was they marketed this. This became a very potent anti-cancer chemo is chemical therapy agent, chemotherapy agent. And so this was the problem with chemotherapy agents is not only will they kill cancerous cells, they could kill healthy cells also. And this particular chemotherapy agent, it's because of the cis, the trans is ineffective, the cis. And the cis, what it can do is bind in the grooves of the DNA. So the two chloros end up binding into the groove of the DNA and get stuck there. And so nothing can replicate. So that's a pretty interesting story for that. Now, here we aren't going to have this because ethylene diamine. With ethylene diamine, we can't attach those on opposite ends of the molecule. Ethylene diamine is not long enough to reach from this end to this end. So ethylene diamine will have to be in adjacent positions. And so, for example, here, if we were to replace the amines with one ethylene diamine, it's not going to work. Because if we put one end of the ethylene diamine here, the other end doesn't quite reach over here. And so ethylene diamine always has to be adjacent. So here it's not a problem. We can put an ethylene diamine, which is NH2, CH2, CH2, NH2 here, and that's fine. And so for ethylene diamine, we only have one structure possible, and that's cis. We can't have the trans. All right, so that's, let's go to D. How do we name D? So aqua or bromo first? Aqua. So this would be penta aqua, bromo, chromium or chromate? Chromium. And the charge? Well, the total charge is 2+, but bromo is minus. And so it's got to be +3. +3 minus 1 gives us +2, the net charge here. Aquas are neutral. And so penta aqua bromo chromium 3. How about this one? E. Rubidium is +1. That means this whole anion here must be -1. And so this is going to be tetrafluoro argentate. Okay, now silver is always +1. But this one can't be +1, because if this were +1, that would be +1 minus 4 gives us -3. If this were -3, then we'd need 3 rubidiums to balance out the charge. So there's a mistake here. That's possible. It's possible that they meant RB3, but silver is always +1. So there's some kind of flag. Or 2, this is an unusual oxidation state of silver. And silver is fixed charge. We learned silver is fixed charge. Silver is always +1. Silver, cadmium, and zinc. Cadmium is always +2, zinc's always +2. And so this one is very unusual. And so let's take a look. And you don't learn about silver 3 because silver 3 is too unstable. These types of things don't last very long. And so silver 3 fluoride containing silver in the unusual +3 oxidation state, very unusual. But there are some other silver 3 species here. Here's this one, the tetrafluoroargentate 3, but this is paired with palladium. And so we do have it, silver 3. Silver 3 is just very odd, that's all, and unstable. Unusual oxidation states, you know, you can get them, but they're usually quite unstable. When I was a student at UCLA, I tried to make one. I tried to make iron 4. What are the common oxidation states of iron? 2 and 3. So iron 4, there's a group of scientists that had claimed to make an iron 4 salt. And so I just tried to repeat that. That's normally what's done. You repeat it and see if you can add something to the knowledge base. And so I was working a lot with fluorine. In fact, this is why I was using liquefied fluorine at very high pressures and temperatures, was to make this iron 4. I thought the experiment went pretty well, and I tried to take apart my reaction vessel, and it was in a glove box, you know, one of these. But I couldn't, you know, with the wrenches, I couldn't unscrew the lid of my reactor. And so I tried all kinds of things to break it free inside the glove box, but was unsuccessful. And finally, I gave up of trying to break it free in the glove box. So I removed it from the glove box. You know, it was okay because it was sealed. And then took it downstairs. In the basement of the UCLA Chem building is a machine shop. So I took it down to the machine shop and tried to break the lid free. I just wanted to break it free, but not break the seal. So I just wanted to loosen the nut a little bit and then bring it back into the glove box and then open it. But what happened was, when I broke it free, the whole thing came off, exposing it to air. And in the short time between, you know, it was supposed to be like a green solid, and I did get a green solid, but it didn't last long. It only lasted a second, and then it decomposed immediately in air. So I think I got it, but unfortunately it didn't, and I couldn't characterize it. And so characterize means just measure its properties and see if those properties match what they claimed. Anyway, that was my last experiment there. I wanted to repeat it, but there was no more time. That was it. And then I left UCLA. But anyway, there are some unusual oxidation states, but a lot of these things don't live for very long. You know, they'll just decompose in a second. Whereas silver in the +1 is stable. We don't have to worry about that decomposing. Sometimes it's stabilized by the ligands, you know, unusual oxidation states, like gold 3. Gold 3 is stabilized by chloroligands. You remember aqua regia? Aqua regia, the HCl was not used as an acid. The HCl was used for the chloroligands, and the chloroligands help stabilize the gold ion, the gold 3 ion. Otherwise, gold 3 is very reactive, extremely powerful oxidizing agent, and wouldn't be stable otherwise. All right, let's take a look at F. What's F here?
Sodium and potassium.
it boils down to what do you call NO? You know, NO would be nitrogen monoxide, but as a ligand, we give it another name. As a ligand, do you know what we call it? Or what we used to call it. Like, for example, carbon monoxide. Carbon monoxide is an excellent ligand. And so carbon monoxide is not called carbon monoxide as a ligand. So if we have iron, let's say we have iron 2 in blood, the normal the normal ligand for iron 2 is oxygen, O2. Would you expect O2 to be a very good Lewis base or a very good ligand? Do you expect O2 to be a very good ligand? No. No. Because what do we want in the ligand? We want a negative charge on the oxygen. Is there any negative charge on the oxygen? No. The oxygens are 0. Both of them. So it's not a very good ligand, but that's good. Because if O2 were a good ligand, it would bond and it would not break off. For blood, you need O2 to bind and then you need it to break off. Eventually. What if we have O2 and cyanide competing for iron 2? Which one would win, O2 or cyanide? Cyanide's going to win. And when cyanide bonds, when it bonds, it doesn't break off. It's on there permanently, or more permanently. I guess you could eventually get rid of it. How about carbon monoxide? Carbon monoxide, also an excellent ligand. When carbon monoxide bonds, it doesn't break off, or it doesn't break off easily. And so this one we call cyano. Oxygen, I don't know what we'd call oxygen, the ligand. We'd probably just call it oxygen. So here's hemoglobin. There's one, it's octahedral. There's one empty spot. That one empty spot is taken up by O2, oxygen. If we are competing O2 versus cyanide, cyanide's going to win. Here. O2 versus carbon monoxide, carbon monoxide is going to win. Let's see if CO's more. Carbon monoxide is a ligand we call carbonyl. Let's go ahead and put that here. Carbonyl. Okay. And so, carbonyl complexes are very common. Carbonyl is an excellent ligand. NO is very similar to this nitrogen monoxide. And so NO used to be called nitrosyl. So we have carbonyl and nitrosyl. This is the old name. Do you know what the new name for this is? Now, if you go to Wikipedia, there are lots of metal nitrosyl complexes. So NO is an excellent ligand. here. So we have some cyanoligands and the nitrosyl ligand here. The new name for this is oxidonitrogen. I think that's a new name. Oxidonitrogen. Wikipedia hasn't caught up. So let me show you. Some of these names have common names like water is aqua, ammonia is amine with 2 M's, CO is carbonyl, NO used to be nitrosyl for decades. They called it nitrosyl. And then some committee decided to change the name to oxidonitrogen. So you're going to find most of the old stuff is going to be called nitrosyl, and I don't think any of the new stuff is called oxidonitrogen. In fact, this is such an awkward name. I don't know why they decided to change it. Me, nitrosyl is just fine. You know? In fact, I don't want to even deal with it. So oxidonitrogen and nitrosyl, I'm not going to put that on any test because, you know, it's awkward. This one used to be called methylamine because that's the name, methylamine, but now they call it methanamine. Methanamine, it's needless additional memorization. We could just call it the methylamine ligand. This is normally called pyridine, so it's called the pyridine ligand. Most ligands are just the normal name, like oxygen. If we have an anion, then we add the O on the end. And so this, for years, was fluoro, but now they changed it to fluorido. For years, this was chloro, and now it's chlorido. I don't even know if Wikipedia is caught up to this. Let's see. So nitrosyl complexes are common, but let's see if they have chloro complexes. Yeah, they're still using chloro. They haven't switched to chlorido. So I haven't quite switched either. I prefer chloro over chlorido. It's just preference. You could use either. I don't care. Anyway, let's go back to our book and then finish these off. So let's name this using the new name. So naming this using the new name, this would be sodium pentacyano oxidonitrogen iron or ferrate. Ferrate, what's the charge? 3. So if it's 3, that's correct. Plus 3 minus 5 is minus 2. This one is neutral, and that's plus 2 from the sodiums. So this would be sodium pentacyano oxidonitrogen ferrate 3. The old name would be sodium pentacyano nitrosyl ferrate 3. Okay, write appropriate formulas for the following. Potassium hexacyanidoferrate 3. So we'll go through these together, and then at home you can just try to go through them again and make sure you can do it on your own. But here we just have normal potassium ions, so just K plus. And then we're going to have hexacyanidoferrate. And so hexacyanido is cyano or cyanido, either. I call it cyano, but I haven't quite updated to the new nomenclature scheme. And then it's ferrate, so it's iron. And then we have 6 cyanides. And what's the charge on this, the total charge? 3 minus. And so how many potassiums will we need? 3. And so we're going to get is K3 FeCN6. Yeah, that would be potassium hexacyano or cyanido. Right, 3. B, bis-ethylene diamine copper 2 ion. So bis-ethylene diamine copper 2. So what goes first, the ethylene diamine or the copper in the formula? Copper. And then the formula for ethylene diamine? The abbreviated?
En.
En. How many?
2.
2. Charge on this? Just this ion. Yeah. 2 plus is correct. All right, this is square planar, and so we're going to have 2 ethylene diamines to it, and they have to be adjacent. So here, NH2, I'll write it out, CH2, CH2, NH2. That's 1 ethylene diamine. The other ethylene diamine will be over here, NH2, NH2, CH2, CH2, NH2. So we got 2 ethylene diamines on there. This whole thing carries a charge of 2 plus, and it has a square planar structure. We could have different anions on this cation. Okay, C, penta-aqua hydroxido aluminum 3 chloride. So chloride, we know, chloride's just Cl minus. I don't know how many we have because we need to know the charge of cation. The cation's a bit more complicated. What is the cation here? Aluminum. Okay, then hydroxide or aqua? Hydroxide, so it's anion, and then aqua. And how many aquas do we have? And what's the net charge on this? Yeah, 3 plus minus 1 is 2 plus. So it's 2 plus. How many chlorides am I going to need for this? 2. So the correct formula will be AlOH H2O 5 Cl2. That would be the pentamine hydroxido aluminum 3 chloride. We don't need parentheses around the hydroxido. We only have 1 of those, so it's okay. D, amine chlorido bis ethylene diamine chromium 3 sulfate. Try this. Actually, let's go back to this. What's the coordination number of this? Why did I put the hydroxide first here? Because anions come first. Anions come first since the 9th edition. Prior to that 9th edition, the neutrals came first. And so they changed the rule. It used to be all the neutrals first, and then the anions, and then they switched it to the anions. I don't know why there's so much change and disagreement with these. They should just keep it simple. They should just do it alphabetical, alphabetical both in the name and the formula. It's going to be easy for. About 10 years ago, it was neutrals first. Maybe next year they're going to go back to neutrals first. Who knows? Maybe next year oxidonitrogen will be renamed nitrosyl. So nomenclature for these is a bit more varied. Therefore, I'm not so strict about nomenclature for these. Not as strict as some of the, other things like calcium sulfate or whatever else. All right, so what do we write first here? The sulfate's easy. That's just regular sulfate. It's not a sulfate though. It's sulfate, which is also 2 minus. What's the cation though?
Chromium.
Yeah, chromium. The metal comes first, and then we need to put the anion ligands next. Are there any anion ligands? So when I look at this, I have chromium first, and then I look for anions. Amine, neutral. Chloride, anion. Ethylene diamine, neutral. And so I know what has to go next. What has to go next is the chlorido or chloro. That goes next. But now I have a choice. Either the ethylene, diamine, or the amine. Which one should I write next? Because both of those are neutral. Well, if I have 2 neutral ones, I'm going to rank those alphabetically. And so it's going to be A for amine or E for ethylene diamine. We'll do A for amine. And then ethylene diamine, how many of those do I have? 2. Now, I don't want to get confused here because I don't know if this is a chlorine bonded to the nitrogen. Sometimes I could have things like this. Where this is the ligand itself. So to prevent that confusion, I'm going to write parentheses around ammonia, even though I only have 1. That way I know for sure this is a chloro ligand and this is a amine ligand, not something like, chloro ammonia. Okay, what's the charge? Oh, is it 2 plus? Okay, then that makes it nice. Because if it's 2 plus, then it's 1 to 1. And so we'll go chromium, ClNH3, En, 2, SO4. 1 to 1. Okay, the last one here, tris ethylene diamine, iron 3, hexacyanosyl ferrate 2. So tris ethylene diamine, iron 3. So we're going to have iron, and then how many ethylene diamines? 3. And what's the charge on this? Yeah, 3 plus. Okay, now that's a complex cation. The anion is also complex. This is 88 ferrate. And so hexacyano or hexacyanido, same thing. It's going to be FeCN6. What's the charge? Well, iron is plus 2. Cyanide is minus 1 times 6 is minus 6. So plus 2 minus 6, 4 minus. 4 minus. And so how many of each do I need to balance out the charge?
4 and 3.
Yeah, so I could just do this cross multiplication thing. 4 of these, 3 of these will give it to me. And so I'll do FeEN 3, 4, which is going to be 4 times plus 3 is plus 12. And then FeCN 6 And I'll need 3 of these, which would give me minus 12. 3 times negative 4. And so this would be the compound here. Okay, I was going to start chapter 15 today, but I'm going to hold off. We'll start chapter 15 next week. What we're going to do now is check-in. And the check-in procedure is this.